Alrighty, hope you all are doing well today. We are going to be talking about basic electrical quantities. And so what we are going to be discussing is the different types of signals and things like that that we're going to be dealing with in this class. So the first one that I want to talk about is voltage, because that's probably the electrical quantity you're most familiar with. Okay. So I'm going to hit you with a mathematical definition here. And if I'm being entirely honest, we're really not going to use this mathematical definition in this class, but it's going to lead us to two other definitions that will help you better understand what voltage is. So the mathematical definition for voltage, I'm going to write V BA is going to be equal to the integral from A to B of the electric field vector E dotted into some differential line element DL. Now, like I said, this definition isn't of particular use to most of us, especially in this class, because we don't really deal with electric fields a whole heck of a lot in circuits 1. In our later electrical engineering classes, we'll use electric fields, magnetic fields, coupled electromagnetic fields, all that kind of good stuff. But here in circuits 1, we tend to have a more simplistic look at things. Okay. The reason why I'm hitting you with this particular definition is because we can very slightly manipulate it into something that we are familiar with that will help us get a better idea about the role that voltage plays in circuits. So another relationship that I'm going to introduce here is Coulomb's law. F, our electrostatic force, is equal to Q, the charge of an electron, times our electric field vector. So if we substitute this relationship for force into our voltage equation, what we're going to have is 1 over Q times the integral from A to B of our electrostatic force, F sub E, dotted into our differential line element. So what does this part of our equation for voltage represent? Does anybody have any ideas? Not hearing anything, so let me make sure my volume is turned up. It seems to be. Somebody's talking in chat. Let's see. Work. Absolutely right. So the integral of force times distance is absolutely work. So that brings us to our first definition for voltage. Okay. Voltage is the amount of energy, same thing as work, required to move 1 coulomb of charge from, point A to point B in a circuit. Okay. So anytime we observe a voltage, then we have to be dealing with some type of transfer of energy because we're moving charge from one point in a circuit to another point, and it requires some amount of work to be done to do so. We can also see from this definition the unit of voltage, right? So I'm going to define the unit of voltage as a joule, which is a unit of energy, per coulomb, and we're going to call this a volt, which has a symbol V. Okay. Another way that we can look at this mathematical definition to help us in our circuit analysis is to understand what a line integral really is, right? So if we have a conservative force, which we do, then a line integral is path independent. And so what I mean by that is it doesn't matter what route we take to go from point A to point B in our circuit, we are going to get the same answer either way. So another way to think about voltage is the difference in electrical potential energy between two points in a circuit or network. Okay. So voltage is nothing more than a difference in electrical potential energy. So one way that I like to describe this is by using gravitational potential energy as an example. So let's consider a very poorly drawn table here. So this is supposed to be a table. Well, if I put an object on the table, it has some amount of potential energy, right? So gravitational potential energy, if you'll recall, is mass times the acceleration due to gravity times the height. So if we consider the surface of this table to be height 0, and we were to raise this ball or whatever to some height h above the surface of the table, we have imparted some potential energy on the system. Well, voltage is literally the exact same thing, but instead of gravitational potential energy, it's electrical potential energy, which means whenever we see a voltage, that means that one point in the circuit is at a higher potential energy than some other point. So these are our two definitions for voltage that we're going to use in this class. And this second one is the one that's going to be utilized the most. Okay, that's the one we're going to see the most. It's the one that's going to be the most helpful, but it's also important for us to understand that whenever we have a voltage present, we are performing work by moving charge around as well. Okay. So now let's talk about how we are going to observe voltages. Okay. So let's say that I have a battery. So this could be, or it's trying to be, a simple AA battery like you might go buy at a grocery store. How much voltage is provided by a AA battery? Anybody know? 1.5 volts. Absolutely right. So a AA battery, when fully charged, supplies a nominal voltage of 1.5 volts. Okay. So that is the magnitude of the voltage that's provided by the battery. But one other thing that we need to pay attention to is the polarity of the battery. So in your Engineering 120 series, you dealt with voltage rises that were provided by sources and then voltage drops that occurred across resistors. That to me is kind of an incomplete look at things. It'll get you through some of the things that we're going to do, but as we get into more complex circuits, that limited scope is going to be problematic. So instead, I am going to officially define polarity here. In a battery, the short nubby bit, what I have drawn on the left-hand side, is the positive polarity terminal of the battery, and the wider bottom is the negative polarity terminal of the battery. So what we actually have is a system where the electric potential energy here is 1.5 volts larger than it is over here. So for the purposes of this class, we have not fully defined a voltage unless we have specified its magnitude measured in volts, as well as its positive and negative polarity terminals of our element. And so that brings us into our next topic, how we are going to represent voltages in a circuit. So the first way that I'm going to show you guys is the American style of representing voltages. So let's say that we have a simple generic circuit element A. And I'm going to define the voltage drop across this element A to be arbitrarily 5 volts. Okay. So this is the American style. We've specified the magnitude, and then we specified the positive polarity terminal by putting a plus sign. We've specified the negative polarity terminal by putting a minus sign. If we wanted to swap our polarities, meaning if we had positive polarity on bottom and negative polarity on top, we would need to change the sign on the magnitude. So anytime you're dealing with a negative voltage, all that really means is that you've assigned the wrong polarity to the terminal. Okay. So if we have -5 volts and we want it to look like +5 volts, we simply swap the positive polarity for the negative and vice versa. And this is probably something that you guys have done experimentally whenever you were measuring voltages in your previous classes, right? If you ever measured a negative voltage, you simply swap the leads of your multimeter, and then all of a sudden you have a positive voltage. Well, it's because you're changing which one you're assuming to be at a higher potential than the other. So now let's deal with the European style. Okay. So I have my same generic circuit element. In the European style, we have our magnitude, and then we denote the positive polarity terminal as the head of the arrow, and the negative polarity terminal as the tail of the arrow, right? So if we wanted to swap the polarity of our voltage, we just change the direction of the arrow, and that in turn puts a negative sign out in front of the magnitude. So this is the European style, and you will never see me do this again. I'm introducing this to you only because you may choose to supplement what you're learning in this class with YouTube videos from other people. And some of those people might use this convention. So I want to make sure that you understand what's going on, but I won't use it again. Now, one that I will use is what's called a double subscript notation for voltages. So once again, I'll have some generic circuit element A. I'm going to call this terminal 1 and this terminal 2. And I could say that the voltage drop across this element, V12, is equal to 5 volts, where the first number in the subscript denotes the positive polarity terminal, and the second number in the subscript denotes the negative polarity terminal. If I want to swap the polarity, I simply swap the order of the subscripts, and in this case, that would give me negative 5 volts. So this is what's called a double subscript style. And we will use this notation a little bit in this class. Once you get into your later electrical engineering classes, and you have complicated systems, specifically three-phase circuits and things like that, the double subscript notation becomes much, much more widely used. So the overwhelming majority of our time in this class, I will be using the American style to denote voltages. So just to be clear here, we need a magnitude and a polarity to fully specify our voltage. So these are the different representations that we use to represent voltages that we are measuring in our circuits. Before we move along to the different types of voltage sources that we might see or how we supply voltages to our circuits, are there any questions? All right. Nobody's saying much of anything, so we will move along to voltage sources. So I'm going to start with a battery, which you all have likely seen the schematic symbol of before. So this is the schematic symbol for a battery. Technically speaking, this is the schematic symbol for a multi-cell battery. If it only has one long bar and one short bar, that would be for a single cell battery. The positive polarity terminal is denoted by the long bar, and the negative polarity terminal is denoted by the short bar. And then the magnitude is typically given as a constant term. And whenever I'm dealing with constants, I tend to use capital letters. So this is a capital V subscript S, denoting a source voltage. Okay. So this is a representation of a battery, which you guys have all seen before. The next one that I'm going to introduce to you is the generic DC voltage source. In our DC voltage source, the positive polarity terminal is denoted by the plus sign. The negative polarity terminal is denoted by the minus sign, and we typically specify its value as a constant quantity as well. So it'll use Vs. In this class, I usually use this generic DC voltage source representation for all voltage sources, including batteries, because when we start dealing with capacitors and things like that, which has a very similar schematic symbol, Having batteries and capacitors in the same circuit can look confusing if you're not paying attention, whereas the DC voltage source symbol is specific. Later on in this class, we will deal with AC voltage sources. And so an AC voltage source is the exact same thing as a DC voltage source, except that there is a little squiggle in the middle, where the squiggle represents that the voltage is changing with time. So this is our AC voltage source symbol. And because our voltage changes with time, I typically denote the voltage in lowercase script. So lowercase is used for time varying quantities, uppercase is used for time constant quantities. And all three of these voltage sources are what are called independent sources. So in an independent source, in this case, voltage for independent voltage sources, the amount of voltage that is being provided by these sources is constant regardless of what is connected to the source, right? So a battery still has, or a AA battery still has a voltage of 1.5 volts, even if you don't connect it to any sort of external circuit. So it would be an example of an independent source. The last two sources that I'm going to introduce are dependent sources, and their value depends on other things that are connected to the source. So dependent sources are denoted by diamond shapes. And we're going to have two dependent sources with the exact same symbol, which can be a bit confusing. So we're going to talk about them here really quickly. This one on the left, I'm going to call a voltage controlled voltage source. And this one on the right will be a current controlled voltage source.
Is there supposed to be any visual difference to both of these?
So I'm about to show you, I guess, what the difference is, because right now there is no difference whatsoever. So you're 100% correct that it's a bit odd that they have the same symbol. So typically speaking, a voltage controlled voltage source, you'll know it's a voltage controlled voltage source because there will be some number K, I'm calling K right here, just an arbitrary constant, multiplied by some voltage elsewhere in the circuit, Vx. And this K is the scaling factor for this voltage source, and it has units of volts per volt, okay? For our current controlled voltage source, we are going to have some quantity R, that's our scaling factor for this guy, multiplied by some amount of current, expressed as Ix, where the symbol for this quantity is expressed in volts per amp. Okay. So the only way to tell the difference between a voltage controlled voltage source and a current controlled voltage source by looking at them is to look at whether or not there is a voltage or a current controlling the amount of output of the source, right? The symbols are identical. Okay. So one thing that I want to be super clear about here, because this is something that tends to confuse students. This current controlled voltage source is a voltage source, which means it outputs some number of volts. Whatever R is, measured in volts per amp, times whatever the current IX is, measured in amps, gives us a quantity that is expressed in volts, okay? So just because there's a current here doesn't mean this is a current source. This is still a voltage source. All of our voltage sources have clearly identified positive polarity terminals and negative polarity terminals. So just to be clear here as well, these controlled voltage sources are examples of dependent sources. Are there any other questions about voltage sources?
The only thing I had was the voltage versus the current, but you answered that, so thank you.
All righty. Okay, so if we're all clear with the, so actually, let me recap here really quickly what we have talked about to this point, okay? So I've introduced the concept of voltage. I've given you a mathematical definition, which we pretty much will never use. We have used that mathematical definition to give us two, I guess, word-based definitions. Voltage is the amount of work done or the amount of energy needed to move 1 coulomb of charge from one point in a circuit to another point in the circuit. We have also found that voltage can be given as the difference in electric potential between 2 points in a circuit. I've talked about the different ways that we are going to represent voltages in our circuits and diagrams. And I've introduced the different types of voltage sources that we are going to see in this class. So before we move along to currents, is there any last questions? All right. So let's talk now about current and charge. These two quantities are very, very closely related, okay? So effectively, anytime we have charge that's moving, we're going to wind up having some amount of current, okay? So mathematically, current I is the derivative of charge with respect to time. So I'm going to put some labels here. This I represents current, and this Q represents charge. Okay. So because we have a derivative-based relationship, this is really telling us that the relationship between charge and current is based on a rate, right? So we can say that current is the rate at which charge passes a given point in a circuit. Well, we can also, from this relationship, determine what our unit of current should be. Okay. So we have charge in the numerator measured in coulombs and time in the denominator typically measured in seconds. And we call this an ampere or 1A or 1 amp. So this is the unit of current. We can do a little bit of mathematical manipulation. So if we were to know the current and we want to figure out the charge, we can say that mathematically, charge is the integral of the current with respect to time. I want to be very clear here. The T prime notation that I'm using does not mean derivative. Okay. So I'm using T prime as a dummy variable to represent time because I'm about to put T, the instant in time we're trying to figure out what the charge is, as a limit of my integration. And because that variable is showing up in the limits of my integral, it would be confusing to also have it be the variable that we're integrating with respect to. Okay, so this is purely from a mathematical standpoint, me just using a different symbol to represent time so that it's clear what we're doing in our integration. Now, the starting point of our integration is going to be some point in time T naught, which represents a time at which the amount of charge is known. So we're going to add that known amount of charge to the result of that integral in order to determine the total charge passing a given point in our system. Okay. Now, I understand absolutely that this can seem a little bit confusing. So let's look at a simple example here. Okay, I'm going to start by saying current passing through a particular circuit element is modeled as I of t is equal to, let's just say, 5t squared. Amps charge passing through the element at t is equal to 0 seconds is Q of 0 is equal to, let's call it 3 coulombs. Determine the total charge that is passed through the element at t is equal to 2 seconds, right? So we know how the current is behaving. We know what the initial condition on our charge was, so we should be using this equation. And so what we're going to find is that Q at 2 seconds will be the integral from 0 seconds, the point at which the charge was known, to 2 seconds, the point in time which we're interested in, times the integral, the integral over those bounds of 5 t squared dt plus the value of the charge at 0 seconds, which is 3 coulombs. So that's going to look like, let's see, so we're going to have 5 amps per second squared. So we weren't given these units explicitly, but if time is measured in seconds, then that, and we're dealing with a current, then that unit, or excuse me, that coefficient of 5 has to have units of amps per second squared. What's the integral of t squared?
T cubed over 3.
Absolutely right. So we're going to have t cubed over 3 evaluated at 2 seconds and 0 seconds. And then to this number, we're going to add 3 coulombs. So I want to be clear here that this 3 coulombs thing is outside the integral. So that's going to look like 5 amps per second squared times 8/3 seconds cubed plus 3 coulombs. So that's going to look like 40 over 3 amp seconds, which is the same thing as a coulomb, plus 3 coulomb is going to be 49 over 3 coulombs. That's the total amount of charge that passed through our circuit element at t is equal to 2 seconds. So this is the level of calculus that I'm going to expect you guys to be able to do in this class. Simple integration of polynomials. We're going to deal with exponential functions, and we will deal with sinusoidal functions, and that is about it. So generally speaking, chain rule, integration by parts, all that kind of good stuff, not entirely necessary. The overwhelming majority of the time, you'll be able to just throw the things that I'm looking for into a calculator and let your calculator calculate your integrals and derivatives for you. Okay, so I'm not trying to say there's not going to be a lot of math in this class. There absolutely will be, but the overwhelming majority of it will actually be algebra based, not necessarily calculus based. Okay. All right, so we have developed, or really I have given you, mathematical relationships between that illustrate how current and charge are related. And I've also given you a definition for current that simply says it is the time rate at which charge passes through a point. Any questions before we talk about representing currents in schematic diagrams? All right. So let's talk about representing current. So if I have some generic circuit element like so, typically speaking, I represent current with a magnitude, let's call it 5 amps, and a direction. So I would say in this particular circuit element, element A, that I have 5 amps of current flowing down, right? I need both the magnitude and the direction to fully specify the current. It is not enough to just say that there are 5 amps of current flowing through the element. I need to know the direction as well. I could represent this exact same current as negative 5 amps flowing up. So if I ever am dealing with a negative current, it really just means that I've assumed the wrong direction for current flow. Okay. So for voltages, we need to specify a magnitude and a polarity. For currents, we need to specify a magnitude and a direction. All right. Now let's talk about the, and there's really only one style of representing currents that we'll deal with in this class, and it is this one. So all the currents that we see will use this general style. Right? So now let's talk about the different types of current sources that we will see. So we're going to start with a generic current source, DC current source. Like so, where the direction is indicated by the direction of the arrow in the middle of the symbol. And then I'll specify the magnitude with this IS, where the I is for the current, the subscript S just means that it's the current being supplied by a source. Okay, so this is our DC current source. The AC current source is going to be the exact same symbol, except that once again, we put a little squiggle through it to let us know that we have a time varying current. And because we have a time varying quantity, I will represent the magnitude using lowercase script. These are our independent sources. And much like the voltage sources, we will also have two examples of dependent current sources, which will have identical schematic symbols. On the left, we have a current-controlled current source. And on the right, we have a voltage-controlled current source. So our current-controlled current source, the direction is obviously specified by the direction of the arrow. So we are going to have K, some scaling constant, times IX, where the units of K in this case are amps per amp, or a unitless quantity. And for our voltage-controlled current source, we are going to have a scaling parameter G, which represents the transconductance times Vx, and the units of our transconductance or scaling parameter is amps per volt. So once again, these are both current sources, regardless or not of whether it's controlled by a voltage or a current. So hopefully this is obvious, but the easiest way to tell the difference between a current source and a voltage source, because they have similar symbols, is if it has a plus and minus sign, it's a voltage source because the polarity is indicated. And if it has an arrow, it's a current source, which means that the direction has been indicated. Okay. All right, so I've talked about what I wanted to talk about regarding currents. So before we move along, does anybody have any questions about currents, representing currents, or current sources?
Wait, does it change the math whenever we start working problems, or should I just wait and see?
What do you mean by does it change the math?
So like what, so just excuse me for being frank, but why do I care if something's a current or voltage source, whether it's independent or dependent? Would I just need to identify it in a problem, or would I need to implement it somehow?
Okay, so I follow you. Okay, so it's definitely going to change the math, and it can also actually change the type of analysis that we're going to wind up employing to analyze a particular circuit, right? So
Okay.
for example, if we have a current source in a circuit, it's probably going to be easier for us to use Kirchhoff's current law in some instances because we have a fixed amount of current entering a particular node, whatever node our current source is connected to, right? And similarly, whenever we have voltage sources, it might be easier for us to use Kirchhoff's voltage law because we know that there is a fixed voltage between two nodes, which is forced by the voltage source. So it'll absolutely have a large impact on how we choose to analyze the circuits. That isn't to say there's one way to analyze any particular circuit. That's one of the best things and also the worst things about circuit analysis is there's usually 3 or 4 different ways to get the same result. But if we can easily identify things and we have a good understanding of the basics, Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, things like that, it'll definitely make the process of analysis easier. So I hope that I've answered your question, but putting things into practice will make things a lot more clear as well.
Okay. Could I say that it's knowing these types of sources gives me a hint as to what formula I might use for that circuit?
To some extent, yes.
Okay. I am generalizing, but
yeah, it'll be a good jumping off point. I think I can say pretty confidently.
okay. Thank you so much.
Yep. Any other questions? All right. Well, now we are going to talk about power and energy. So these are 2 other quantities that we're going to be dealing with very regularly. And they are related to each other. Because you guys have all had physics 1, you probably know how they're related to each other. So let's start with our definition for power, right? Power will be the derivative of energy with respect to time. Okay. But we can use our relationships that we've developed to kind of have a different look at things, right? So what I'm about to do is I'm going to expand this derivative. So what if I had the derivative of energy with respect to charge multiplied by the derivative of charge with respect to time, right? Well, energy over charge is just voltage, and charge over time is just current. So power can also be expressed as simply the product of the current and voltage for a particular element. Okay. Our word-based definition, if you will, is that power is the rate at which energy is transferred to or from a circuit element. And if we know that power is the derivative of energy, then it stands to reason that energy will be the integral of power. Like so. So we can say that energy is the total amount of power absorbed or supplied by an element over a fixed interval of time. All right, so what I want to talk about now is related to the concept of power and energy. It's called the passive sign convention. And if I am being honest, it is one of the topics that students find the most confusing in this entire class, okay? And this is something that is so important. You will be both directly and indirectly tested on it in effectively every single homework assignment and exam that you're going to have in this class, okay? I'm going to explain it to you as simply and straightforwardly as I possibly can. And for some of you, it will click right off the jump, and that's wonderful. And for others of you, it will literally take weeks of practicing with it before it fully makes sense, but I promise you'll get there, okay? So this is the passive sign convention. In a nutshell. So let's say that I have some generic circuit element A, like so. And I am going to extend the terminals of element A out like this. Okay. Let's say that A is part of a larger circuit. So that's what these ellipses here mean, that this element A is connected to some external circuitry in some way, shape, or form. How that connection occurs isn't particularly important here, okay? I'm going to define the voltage drop across element A as having its positive polarity on top. And I'm going to define the current that's flowing through element A as flowing into the positive polarity terminal. In this case, where the current is flowing into the positive polarity terminal, the power absorbed by element A is IA times VA, and the power supplied, by element A is negative IA times VA. Okay. So at no point did I specify that IA and VA need to be positive quantities here, okay? So it does not matter whether VA is a positive voltage or a negative voltage. Does not matter if IA is a positive current or a negative current. If IA is flowing into the positive polarity terminal of voltage VA, the absorbed power is simply IA times VA, and the supplied power is negative IA times VA. Now let's consider what happens if we have the opposite configuration. So we have our same element A, the set of terminals. Element A is connected to some other circuit. I'm going to define VA be positive polarity on top like so. But now I'm going to define IA such that the current is flowing into the negative polarity terminal. In this case, the power supplied by element A is positive IA times VA, and the power absorbed by element A is negative IA times VA. Okay. This is all the passive sign convention is. Okay. If the current is flowing into the positive polarity terminal and we want absorbed power, we leave it with a positive sign. If we want supplied power, we add a negative sign. In the opposite case, when the current is flowing into the negative polarity terminal, if we want supplied power, we leave it with a positive sign. If we're asked to find absorbed power, we introduce a negative sign. So let's put this into work for us. Let's work an example here. I'm going to draw a circuit. I'm actually going to pull an old circuit from an exam that I've given in this class before. Just one moment here. So this will be our circuit of interest. Here's element A. Here's element B. Here's element C. D. E. F. And G. And now I'm going to specify some voltages and currents in this circuit. Okay. So let's say that the voltage drop across element A with positive polarity on top is 12 volts. The current flowing down through element A is negative 2 amps. Let's say that the voltage drop across element B is 4 volts with positive polarity on the left. The current flowing through element B from left to right is 2 amps. The voltage drop across element C is going to be 8 volts. Let's go over here. I'm having to do a little bit of mental math because we don't yet supposedly know Kirchhoff's voltage law and Kirchhoff's current law. So let's say that we have 16 volts here, 4 volts here. 20 volts here. Let's make this current -1 amp. Let's make this current 2 amps. This current -2 amps. This voltage will be 12 volts. Let's see, I still need 2 currents to label here really quickly. So let's do 3 amps here so that this looks like 1 amp, like so. What I want us to find is the power absorbed by elements A through G. So let's start with element A. What's the voltage drop across element A?
Twelve volts.
12 volts, absolutely right. What's the current flowing through element A?
Would there be 2 amps?
Well, kind of yes and yeah, so -2 amps, as the way that I intend you to read this thing. Getting a little bit ahead of ourselves with possibly Kirchhoff's current law here. So let's say that we're taking the -2 amps to be the current through element A. Is that current flowing into the positive polarity terminal or into the negative polarity terminal?
Into the positive?
Right. So since we're calculating absorbed power and the current flowing into the positive polarity terminal is -2 amps, the amount of power absorbed by element A is -24 watts. Now let's look at element B. What's the voltage drop across element B?
4 volts.
4 volts. What's the current flowing through element B?
Positive 2 amps.
2 amps.
Is the current flowing into the positive polarity terminal or is it flowing into the negative polarity terminal?
Flowing into the positive.
All right, so because it's flowing into the positive polarity terminal and we're calculating absorbed power, we don't add a negative sign, so 4 times 2 is +8 watts. Now let's look at element C. What's the voltage drop across element C?
8 volts.
8 volts. What's the current flowing through element C?
1 amp.
Is the current flowing into the positive polarity terminal or the negative polarity terminal?
It's the negative polarity.
All right, so because we're calculating absorbed power and the current is flowing into the negative polarity terminal, we need to add a negative sign. So we get -8 watts. This is as hard as the passive sign convention has to be. This hopefully does not seem particularly difficult. It is literally find the voltage, find the current. If we want absorbed power and the current's flowing into the positive polarity terminal, we leave it alone. If we want supplied power, the current needs to flow into the negative polarity terminal. All right, so let's keep on going here with element D. So what's the voltage drop across element D?
12 volts.
12 volts. What's the current flowing through element D?
3 amps.
3 amps. Is the current flowing into the positive polarity terminal or the negative polarity terminal?
The negative.
Yep. So we add a negative sign, and now we get negative 36 watts. Let's look at element E. So what should the result for element E be? I'm going to stop writing things down. You guys just tell me what the answer should be.
Negative 32.
So
Oh, the
It's
negative,
positive.
negative 2 amps. I see. Yep, he's right.
yep,
I missed that
positive,
negative on the 2.
positive 32 watts, because while the current flowing through the element is negative, it's also flowing into the negative polarity terminal, which means we need to add a negative sign. So positive 32 watts. What about element F?
That one would be 8 watts.
Positive 8 watts, absolutely right. And finally, power absorbed by element G.
Negative 20.
Negative 20 watts.
I disagree.
Oh, because there's that negative on the 1. So then it's positive 20.
Yeah, because the
Oh,
negative
yeah.
flowing into the negative polarity terminal, we're going to have negative times 20 times a negative 1, which comes out to be positive 20. Do me a favor here, really quickly. Add all these numbers together.
It equals 0.
Equals 0. So that's another thing related to power and energy. It's called Telegen's theorem. And Telegen's theorem simply states that the total amount of absorbed power, I'm going to put in parentheses here, we could also write it as supplied, because to get supplied power, we would simply multiply every one of our numbers by a factor of -1. Excuse me. The total amount of absorbed or supplied power in a system must equal 0. So if we weren't given some of these quantities, technically speaking, we could use Telegen's theorem and figure out, if we didn't know, for instance, the current flowing through this element G here. Well, if we figured out the powers absorbed by elements A through F, we would know that whatever power was absorbed by element G would be whatever it causes to make that total sum equal to 0. Since we were specified the voltage, we could then use our power relationship to figure out what the current is. Okay. We'll learn easier ways to do that in our next class meeting when we talk about Kirchhoff's voltage law and Kirchhoff's current law, but that is an alternative way to get those results, right? So let me just redraw this. I believe it was -1 amps flowing out. All right, so we have talked about voltage, talked about current, and talked about power and energy. We've looked at a couple of example problems. So there's really only one last thing that I want to do for today's class meeting, and that is to talk to you guys very briefly about a couple of your workbook problems that are a little bit difficult, or at least in my opinion, could be worded better. So I'm going to give you guys some hints here really quickly. So let's look at homework set number 1. Let's look at problem 1 here. So this is just charge and current relationships. The only thing that might be remotely problematic here is part D. It's asking you about average current. The average current is going to be nothing more than the total amount of charge divided by the duration of that interval. So literally just the answer from part C divided by whatever, for these numbers, 17.3. I'm guessing seconds, although the units aren't specified. So nothing particularly weird there. Just expecting you to know how to calculate the average value of a time varying function. So it's just similar thing here. The total energy, let's see, you have voltage, you have power. So the total energy is just going to be the integral of the area under the curve here. The average power is just going to be that total energy divided by the duration, the time. Do notice, however, power is measured in joules per second. The time here is expressed in minutes, so you will need to convert. There are 60 seconds in every minute. So there's a little bit of unit conversion going on there. The average current should be nothing more than the average power divided by the voltage given. So nothing too wild or terrible there. For problem 3 here, this is really going into the passive sign convention stuff. So for instance, if we look at element A, we can see that the current is flowing into the positive polarity terminal. So V1 times I1 is the absorbed power. We're asked to find supplied power, so remember to multiply by a factor of -1. Literally what we just did. Nothing wild or crazy there. Problem 4 here, let's see. We're given a mathematical expression for charge. We're asked to find charge. Then we want the maximum charge. How do we find the maximum value of a function?
You solve for y, right? And then you get, once you get like a positive, you could get a positive, negative value, and a positive value. That's a guess.
How I learned how to find the maximum or minimum of any function was to take the derivative and set the derivative equal to 0. So you're solving for the time at which the derivative will be equal to 0. And then the positive or maximum value is just substitute that time back into your expression. So you should be able to take the derivative of that Q of t, which is really the same thing as finding the current. And then whenever the current is equal to 0, will tell you the time at which the maximum value of the accumulated charge is, and then from there you should be good to go. Right, so it's actually looking for the time and then substitute the time in to get the maximum charge. And then the rate of charge accumulation is literally the derivative. And then this problem 5, this is the one that I actually get asked the most amount of questions about for this particular homework set. And it's because it is worded poorly. So it says, which of the DC sources above are supplying power? For some of you all, it will say which of the DC sources above are absorbing power. There is a word that is effectively missing here. It wants to know whether that is supplying or absorbing positive power. Okay, so we can look at this really quickly here. let's just look at the source V1, okay? So whatever current I2 has is flowing into the negative polarity terminal of V1. So if V1 and I2 are both positive quantities, then V1 is supplying power. V1 is positive 8.5 volts for me. I2 is positive 1 amp. So I should check the box for V1. Now let's look at source I2. The current I2 is entering the positive polarity terminal of V2. So if I2 and V2 are positive, I would check that, so I2 is entering into the positive polarity terminal. So I2 times V2 is absorbed power. So if either of those are negative, I will have positive supplied power. Since V2 is negative and I2 is positive, it looks like V2 is supplying, I2 is supplying positive power. My finger can't work there. For V3, let's see here. So I3 is entering the negative polarity terminal. So if V3 and I3 are both positive or are both negative, then the answer would be positive. V3 is positive, I3 is negative, so that one is actually absorbing power. For current source I4, the voltage drop across I4 is the same as V3 because those two things are in parallel. So we need either V3 or I4 to be negative. V3 is positive, I4 is negative. So that means I4 gets checked. Let's look at V5. So the current I6 is flowing into the positive polarity terminal. So we want either V5 or I6 to be negative. V5 is positive, I6 is negative. So it looks like V5 gets checked. And then lastly here, we would have the current I6 flowing into the negative polarity terminal. So we want V6 and I6 to both be positive or both be negative. Only one of them is negative, so we don't check that one. And let's just check our answers here. All correct, right? So the word positive is missing from which of the DC sources are supplying positive power here. And that same word positive is missing if you have the absorbed variant, okay? All I did for this was the exact same thing that I did for the example problem we just worked. Just looking through here, multiply the voltage times the current because we were finding supplied power. I was looking for the current flowing into the negative polarity terminal. All right, so unless you guys have any questions of me, I think we are done for today.
I actually do have one question. It's like at the very beginning when you're doing like the distance thing for voltage.
Sure.
So does that have something to do for like, because like I know like, I'm not sure if this is actually a factor or not, but like, does your voltage drop if you're running like a really long wire?
Yes, absolutely. Well, so under the assumption that there is current flowing in the wire, then yes. So we're going to talk about that at the beginning of our next class meeting when we talk about Ohm's law. We'll be talking about the concept of resistance. Resistance, just as a very quick thing here, we'll get into this in much more detail on Wednesday or no, tomorrow. But resistance is a measure of how easily or how difficult current is able to pass through a particular element or material. And the length of the material, like a wire, tends to increase the resistance of the wire. And so the longer our wire gets, the larger of a voltage drop we will see for a given amount of current.
All right, I just wanted to confirm my suspicion because I watch Electro Boom. You know who that guy is, right?
Yeah, that's the guy. I think, is he the one? Is he like maybe an Indian fellow or Pakistani fellow? Or something?
He's like an Iranian Canadian guy.
A different guy that I'm thinking of. I saw this video of a guy who was trying to pass, I think, a large amount of current through graphite rods one time and was causing them to explode and was swearing and cursing a lot while he was doing it. And I found it very amusing, but I don't
Yeah,
remember.
it's definitely him.
Yeah. So it's been so long since I saw the video, I guess I forgot what his nationality was or whatever. But yes, the short answer is yes. The length of your conductors can play a large role, especially in larger systems, right? So if you're going to go out into industry where you might be, running cable runs over several hundred yards through conduit and all this kind of stuff, you actually need to really pay attention to the size of the conductors that you use, because if they have a larger cross-sectional area, they tend to have a smaller resistance, which means you can get away with using longer runs without seeing appreciable voltage drops. And we'll talk about that a little bit on tomorrow's class.
All right, that sounds good.
Yep. Anything else?
No, I'm good. Appreciate it.
No problem.
Hey, so I've got a question.
Yes, ma'am.
So the in-class assignments, I know that we have already had one class. So this is technically our second class meeting. So is our in-class assignment 1 due before the next class? And if so, how do you want us to submit those?
Okay, so fantastic question. The first in-class assignment that is assigned for this class is over the material that we've covered today. I am going to have it due, I think by 2 p.m. on Wednesday. I might actually push it back one extra day to give me a little bit more time to get videos uploaded for the people who are taking the course asynchronously. I think I will do that. I think I'll make it 3 days out. Just to give you guys a little bit more breathing room and all that kind of good stuff. There will be submission portals set up on Moodle. I meant to do that today and I got distracted working another class that I'm teaching this summer. So I'll get your first couple of submission portals up as soon as we wrap this class meeting up, so that you have a place to turn in your first few in-class assignments, and then I'll work on getting all of them up over the next few days. So everything will be submitted digitally. So there will be a little assignment on Moodle below where in-class assignment 1 is. So that would be for today's class meeting that you'll be able to submit your work to. And then I will also have it set so that the solution to the in-class assignment, which is just how I happened to work it, it's not the only way to work these things correctly, but I'll have my solutions available to you all as well as study material. Did that answer your question?
Yeah, it definitely did. Thank you. I appreciate it.
No problem. Any other questions?
So the in-class assignments, if I remember right, you said that they were intended to be done collaboratively. Is that correct?
Yeah, so ideally you guys could form little groups here in Zoom, or I think I can use like breakout rooms and all that kind of stuff. I'd have to figure out how to do it. But yeah, it's not necessarily an individual assignment. So like in a standard classroom meeting, typically each table, either everybody at the table works together, or maybe if it's a large table of students, say 6 or so, they might split off into 2 groups and talk to each other about how to work the problems and all that kind of good stuff. Whatever works for you will work for me. I do want to reiterate that these are not graded on completeness or correctness. And so what I mean by that is, as long as it looks like you're giving it an honest attempt at trying to get things right, you're not just writing down garbage or turning in assignments for other classes, which has definitely happened before, you will get full credit as long as you turn something in.
But would you be opposed? It sounds like not, but I'll just ask, to me setting up a Discord server and then just handing it off to you after the class or something like that.
No, that is perfectly fine. Yeah, so if you guys want to set up a Discord server or a group me or something like that, I have no problem with it. The only thing I would say is that I don't want to be invited to it.
Okay.
Purely because I feel like you guys need a place to be able to talk crap about me behind my back.
Okay, fair enough.
Needed. Yeah, I want you guys to be able to vent and discuss things without me hearing any stuff that you might not want me to hear.
All right. Thank you.
Are you going to make the Discord server right now, or like post a link?
Yeah, I'm working on it. Yeah, let me just see if I can do it real quick.
All right, bet.
This is 222, 221.
This one's 221.
Thank you. Copy. That should work.
Let's see. Oh, yep. It came up.
Great. Okay. I'll customize it and whatnot. Dr. Crittenden has one, so I'll just model it after his. Yeah, okay.
Everyone's coming in.
Well, I'm gonna get started on the problem now.
I'm gonna hang out on Zoom here for the next few minutes and all that kind of stuff. I will be setting up the submission portal links. But I do have my volume on, so if you need anything, just let me know.
All right, I'm gonna hop off. Thank you.
Thank you, Dr. Hartman.
You guys are very
Have a
welcome.
good day, Dr. Hartman.
You too.